Hi, and welcome to Section 4, Evolution of NLP Architectures. In this section, you'll learn about the history of NLP and the various architectures that are now used for cloud-based NLP solutions. In this video, you'll learn about three NLP architectures: recurrent neural networks, or RNNs, sequence-to-sequence models, or sec-to-sec, and transformers. Before you learn about these architectures, though, it's important for you to understand some NLP history and to understand the relationship between NLP and neural networks. NLP problems have been studied for a long time. As far back as the 15th century, there were philosophers and mathematicians who proposed the creation of a system for translating between languages with code. During and shortly after World War II, mathematicians proposed using some of the encoding techniques developed for military purposes to create automated translation machines. One of the well-known artifacts from this period is the Turing test, which was developed by Alan Turing in 1950. The Turing test determines whether a machine exhibits intelligent behavior that can't be distinguished from human thought. The lack of a linguistic model was a major stumbling block for many of these early approaches to NLP. This situation started to change in the 1950s. Noam Chomsky published Syntactic Structures in 1957, which introduced the concept of a universal grammar. It was a major step forward in the field of linguistics. NLP became recognized as a computer science problem in the 1960s. Several significant conceptual frameworks were developed between the 1960s and the 1980s. Two of the more significant advances were the conceptual dependency model and the Augmented Transition Network, or ATN. The conceptual dependency model was developed by Roger Schank at Stanford University in 1969. It introduced the idea of deriving meaning from human language independently from the words that are included in the input. Augmented transition networks were developed in a similar time frame and were influenced by Schank's work. ATNs introduced the idea of using recursion to parse sentences. These early frameworks were applied to automated translations, early robots, and applications for specific domains. For example, the Shur-du-Lu system was developed by Terry Winograd at MIT in the late 1960s. It could respond to human language commands to manipulate images of wooden blocks. The 1990s and the first decade of the 21st century saw significant growth in the use of neural networks and the use of artificial intelligence, or AI. Some examples of important early developments include recurrent neural networks, which are also known as RNNs. They can pass learning from one layer of the network to another layer of the network. Other developments include long short-term memory, or LSTM, and gated recurrent units, or GRUs. They're both used to optimize neural networks. And finally, sequence-to-sequence models, or sec-to-sec, were also developed. These early neural networks provided an important foundation for the NLP systems that are now used every day. Initially, it wasn't economically feasible to run neural networks in large-scale production. But the growth of cloud computing changed this situation, especially when it's combined with the ability to scale quickly to very high compute capacity on demand. Cloud computing made it possible to develop the NLP applications that millions of users interact with daily, like Amazon Alexa or Google Translate. New NLP architectures have been developed in the current era. For example, transformers are a new architecture that evolved from sec-to-sec models. Neural networks imitate the way human thinking occurs by creating a collection of interoperating nodes. They are divided into three distinct layers. The first layer is the input layer. It captures the dimensions in the set. The second layer is the hidden layer. It consists of weighted nodes that perform functions specific to the problem domain. And finally, the third layer is the output layer. It provides the results of the processing. Neural networks are applied to a variety of AI problems. You can use a neural network for many types of NLP problems, such as speech recognition or machine translation. You need to run neural networks multiple times before you can find the correct number of nodes and the correct weights for the functions in the hidden layer. During the tuning process, you'll find that some weights outperform others. If you track the improvements in output as you change the weights, you'll have a series of number pairs that match the change in weights to the improvement of the function. If you plotted these changes, you'd produce a line. The gradient would be the slope of the line. A gradient that's close to zero means that your model isn't improving. Networks with higher gradients learn faster. Here's an analogy for the gradient. Imagine that you're climbing up a mountain. Each of your early steps up the mountain would take you closer to your destination than the latter steps because the mountain has a steeper slope towards the top. If you measure the distance between the start and end of each step, you'd have a series, just like the series for the change in weights for the neural network function. Although neural networks mimic human thought, they have some limits. For example, humans don't need to evaluate each input from scratch. You can process an input because you already have a certain amount of knowledge. As you read text or listen to a lecture, your mind can process the input from previous cycles. If you think of this series of inputs to your mind as a long-running sequence, then you have the idea of a feed-forward network. As new inputs arrive, the feed-forward network passes the output to the next series of nodes. The problem with a feed-forward network is that the individual network nodes need a way to use the information that earlier nodes already learned. This is why RNNs were developed. RNNs can use LSTM to remember the information that was previously learned. Here's an example of why you'd need LSTM. Imagine that you're creating a typing application that can automatically complete words. You're also using a simple neural network. When you start entering the word government and you get to the letter V, the application should suggest the rest of the word, which is earnment. Without LSTM, the network can't suggest the rest of the word because it will have forgotten about the letters G and O that came before the V. In the 1990s, researchers who worked with neural networks discovered some problems with managing gradients. For example, accumulating gradients between multiple cycles sometimes resulted in very large updates to the weights that were in the hidden layer. This situation is known as an exploding gradient, and it can lead to an unstable network. GRUs were developed to deal with these problems. Sec-to-sec models were first introduced by Google in 2014. They were designed to address the problem of how to map inputs to outputs, where the inputs and the output sequences are different lengths. For example, say you want to translate the question, "How are you?" from English to Spanish. The English input is 3 words, but the Spanish output is only 2 words, or "¿Cómo estás?" Sec-to-sec models work well for translations because you need to transform the sequence of words from one language into a sequence of different words in another language. LSTM-based modules are generally used for sec-to-sec models because they can give meaning to the sequence, while remembering the parts that are important. A sec-to-sec model consists of a few parts. First, it has an encoder, which captures the input to the model. The encoder is made up of either LSTM or GRU cells. Next, it has an encoder state, which is also known as an encoder vector. This calculates the value for the nodes in the hidden layer. Finally, it has a decoder, which predicts the output based on the input. Sec-to-sec models are used by many systems that respond to human speech, such as Amazon Alexa. The transformer architecture for NLP provides a way to create a sec-to-sec model without using an RNN. It introduces the idea of attention. This concept is another way that neural networks have been adapted to behave more like human thought. When you read or hear a sentence, your brain can evaluate each word in the sequence. Your brain knows that word order is important, so it can immediately infer the meaning of the word in relation to the previous words. So the neural network designer's task is figuring out how to give the neural network this knowledge. The transformer architecture is similar to the sec-to-sec model. However, it replaces the ability of the RNN to retain knowledge between iterations with a layer that retains the position of every word in a sequence. The bidirectional encoder from transformers, or BERT, is a model that builds on the idea of transformers to fine-tune pre-trained NLP models. It's been used to improve the performance of various NLP tasks. Thanks for completing this module. In the next module, you'll learn about how to process text for an NLP application. See you in the next video.